Okay, welcome back. Okay, so this is our last lecture before the Thanksgiving break. There will be no lecture on Thursday. And we will start our new topic on single source shortest path problems. So this is the second type of advanced graph algorithms that we will cover in the rest parts of the graph algorithms as a chapter. Okay, so this is actually a very common problem when we navigate in our map app using the cell phone or maps. So we actually want to need to input the destination, right? And the map app will like automatically calculate the shortest path in terms of time, in terms of traveling the actual distance, and considering all the real-time traffic information, everything put together, we have the short path provided by the map app. And but the backbone data structure that are used in this sort of apps is the graph representation of the whole map. So the destination and the source, the different places, different geographical locations are represented by the vertices in the graph data structure, and the traveling time and the actual distance, for example, are kind of represented by the weighted edges. Okay, so the weight of edges now have very clean specific meanings. So the shortest path problem that we will cover today is the so-called single source, which means we just consider one vertex as our source vertex. And also it's the simple shortest passes that we'll talk about. By simple, we mean that we don't consider the cycles, right? So if there are cycles exist in a graph, actually between the source and the target, if there are cycles, then you can actually go within the cycle for infinite amount of times, so that you have multiple possible passes. But we don't consider that case, and we, for the simplistic reason, to simplify, for simplification purpose, we will not consider the cycles in the past. And we will show in the slides today that if there are cycles in the past and the weight, the summation of weight in the cycle is negative, then the shortest path does not have a valid definition. Okay, our shortest, the path length is defined by the summation of weights of those edges along the path. So if there is a negative total weight, then that value can be infinitely negative, which will be a problem because it doesn't have a minimum values. Okay, so I hope we can cover the first, at least the first uh, the Bellman-Ford algorithm for computing the shortest path. And if not, uh, hopefully we can cover the Bellman-Ford. And if not, I will probably make a makeup video and upload it before the Thanksgiving break, so that you can finish the last assignments in time. Alrighty. Okay. So the shortest single source shortest path, actually, as I mentioned, it's very commonly encountered problems in our daily life. So the destinations and the different locations can be actually represented by the vertex in the graph, and the segmentation, the segments of road connecting two intersections is an edge. Okay, and the length, the physical length or the traveling time can be measured by the weight, can be represented by the weight. Okay, and the graph is typically directed because the one-way roads between connecting two places. So let's lay out all the notations and fundamental basics for defining this shortest path problem. Okay, so we will use a directed graph and also the weight function, which gives a real valued weights. Okay, so how do we define a path? We can represent a path by a sequence of vertices. For example, we have k plus 1 vertices from v0 to vk, and you can think of v0 as your source, and the vk is the destination vertex. Okay, and the summation of all these vertices, of all these edges along this path, to be the total weight of the path, right? For example, the segment from vi minus 1 to vi, and in this case, the weight for that short segment is returned by the weight function. Okay, so this weight function uh, returns a real value given the starting vertex and ending index. So this weight function W, we will meet it later in all the functions we define, because that contains the weight information for the whole graph. So yeah, so W is not, just for clarification, W is not a vertex. It's a function. Okay, and then we will define another notation using the Greek letter delta. So the delta between two vertices from U to V, we use delta U and V to define the shortest path weight. Okay, so delta is a value. It's a real numbered value that measures the minimum weight of the path between U and V, from U to V. Okay, so if there is a path from U to V, okay, so there could be multiple uh, intermediate vertices between U and V. So if there is a path exists, then we find the path that has the minimal weight, total weights. And the weight W of P is defined uh, in the equations above. Okay, so the above equation will be used in this one. So we find the minimal values because there could be multiple weights. And that minimal weight is the so-called shortest path weight. Okay, so if there's no path, that is the U and V is separated, is not reachable. V is not reachable from U. Then we will define the shortest pathways to be infinity. Okay. So this also implicitly claims that a shortest path may not be a unique one. Okay, so from U and V, as long as any path satisfies that its weight is the shortest path weight total, is the shortest path weight delta. Okay, because the delta itself is a value. So as long as the weight of the path is a minimal value, then we call it a shortest path. So there could be multiple shortest paths, but different paths. Okay. All right, and then because we have met the path length before when we introduced the elementary graph algorithms. So when we want to search the graph, first of all, it's the graph searching algorithm. Graph first search, BFS, is a searching algorithm, and it needs to go through edges to reach all the vertices. But in BFS, we also define something, define the length, right? But the the shortest path returned by BFS is defined on using on top of the unweighted graph. So all the edges, they have equal weights. Okay, there's no real number values. So in the case of BFS, the shortest path, if you go to the previous lectures slides, you will find that the shortest path in BFS is defined in a different way. It's defined by the count of edges, by the number of edges, but not the total weight, not the summation of weight, right? So the shortest path from S to T is represented by the number 2 here because there are two edges between S and T. So this is a very clear difference here. But the shortest path that we define here is a summation of real numbers. So we can say that the single source shortest path problem we're going to cover today is actually includes the case for the BFS, because in BFS we can just think of that each weight has equal, each edge has equal weight. All right, so let's look at several different variants of the shortest single source of the shortest path problem. So the one we gonna particularly focus on is the single source shortest path problem, which means that we want to build a shortest path from one given source vertex to each vertex. Okay, so this is a uh, important information here. We are given one source and we want to know the distance from the shortest path from that source to each vertex in the graph. Okay, so this algorithm actually does a lot. It does not just consider one source and one target, but also it's it gives the shortest path, it outputs the shortest path for all the vertices uh, in the graph with respect to the given source vertex. Okay, and there's some other variants like single destination. Okay, we specify destination and we should consider all the other vertices as sources. Okay, but the direction is to the target, not from the target. And there could be like single pair. I think the single pair problem is more uh, often used in when we use our map, right? We just specify our maybe our current location as the source and our destination as the target, as a target vertex. Okay, and of course the all pairs, which means all possible pair paths between all possible combinations of source and destination. This is a more computationally expensive problems. Okay, so here's some just clarification on what type of question, what type of problem we are solving today. All right, now let's further look at an interesting property for the shortest path problem. It's called the optimal substructure. So I hope this term is still sounds familiar to you, because the optimal substructure is something we used, the term we used to describe the property of dynamic programming problems or the greedy algorithm problems, right? It basically says that the optimal solution to the original problem consists of the optimal solution to the subproblems. Okay, and the shortest path problem is has a very typical optimal substructure. Okay, because a shortest path between two vertices must contain other shortest paths within it. Okay, so which means well, if there's a segment that is not the shortest path, then which means that segment could be small, could have smaller weights, right? And that violates the assumption that we already have the shortest path. So this optimal substructure tells us that okay, we can probably use dynamic programming and the greedy algorithms to solve the problem. For example, when we are building a shortest path, we don't know whether the next the edge we will select will lead to the global shortest path, but we can just use the greedy strategy to choose the edge that's minimize the current total summation of the weights, which is a typical greedy algorithm sort. All right, so let's look at this lemma, which is the subpaths of shortest path are shortest path. So we're not going to prove it, but it basically says that um, given the shortest path um, from from the points v0 to vk, so it's already a shortest path. And for any I and j that's between 0 and k, so 0 is at the left end, k is at the right end, and any pairs of vertices I and j, then we let the path from I to j be the subpath. Then we are sure that this subpath is also a shortest path from I to j. Okay, so I think this lemma just naturally is naturally valid, because if this segment is not a shortest path, then the whole assumption from 0 to k is a shortest path will be a unvalid assumption. All right. Okay, so now we gonna look at some special cases about the weights. Okay, so um, I think it's the first time that we look close at the negative weighted edges. While previously we don't actually care too much about whether it's negative or positive numbers for the edges, but uh, when we want to sum up all the weights in a graph, then the negative versus positive differences can really matter. So first of all, we allow the negative edges to exist because, for example, it can carry some meanings, right? It can, for example, the amount of money being transferred from one account to another account, we can use the negative numbers uh, to kind of indicates whether this is a deposit or this is a um, spending, right? Uh, so for the specialty about the negative weight edges is that we want to avoid the negative weight cycles. Okay, so this is something new we're gonna look at today. Okay, so if a graph contains no negative weight cycles reachable from S, then the shortest paths are well defined. So that says we can only make sure that the shortest path weights for all the vertices in the graph can be valid only if the graph does not contain any negative weight cycles. Okay, so this is something we definitely want to avoid the negative cycles. And we will later see in the next slide for a concrete example why this is the case. And if unfortunately we have a negative weight cycle that is reachable from the source, then we have to admit that the shortest path weights are not well defined, okay? And if there's indeed a negative weight cycle on some paths, then we have to define the shortest path to be negative, to be infinity, because the infinity means that it's not a it's not a natural number, it's not a real number. Okay, so let's see from some examples why negative weight cycles is something we want to avoid. Okay, so looking at this graph, we have 8 nodes, 8 vertices, and some edges connecting them. And the first of all, there's a cycle. There are 2 cycles. Well, definitely there are more than 2 cycles, but there are 2 um, very obvious cycles here from C to D, right? And also another obvious cycle from E to F here. And let's consider these passes. So if we, as a comparison, if there's no cycle, then there's only one path from the vertex S to vertex B. So S is here and the B is here, right? The path between S and B is just unique, right? Only consisting of two edges. But if you think of the path from S to C, right? You can see that there is a direct connection from S to C. So that is one path, right? The edge itself is a path from S to C, okay? But we're not done yet because there's a cycle after C. So we can actually go from S to C and then from C to D and then go back from D to C, right? So this time we use three edges to form a path, which can be represented by this sequence of vertices from S to C and C to D and D to C. This is also a path, right? But it just consists of one cycles. Okay, so but we can go infinite number of times to go along that cycle. For example, we can go from S to C to D and to C to D to C, like two cycles and infinite numbers. So anyway, there are infinitely many passes from S to C. We can go in that cycles unstoppably, like as many times as possible, right? So this makes the whole thing very complex because there's no unique path uh, validly defined. But because one good thing about this is that the cycle from CDC, right, from C to D to C itself forms a cycle. The summation of the cycle, if we pay attention to the weight here, it's 6 plus minus 3, which is 3, right? So this is a positive total weight, which means that the more cycles you go, then the higher total weight you will gain, right? So still, because the cycle has a positive cost, so that means you don't want to go through that cycles many times, as many as possible. So there's still a shortest path from S to C well defined, which is the edge from S to C. Okay. Uh, and also the shortest path from S to D here is also defined, which is from S to C and C to D. Okay, this is the shortest path from S to D because you can go for another circle, say SCD, CD, but that additional from from D to C and C to D will give you extra total summation of weight because the cycle's total summation weight is positive. Is positive. So that's fortunate. We can still have the shortest path defined. Well, but the thing will be different if we look at the the second cycle, the lowest part, the bottom pass. And similarly, between S and E, we can have infinitely many passes, like from S to E, and then S, E, F, E. But this time, because the cycle from E to F. Like you start from E and then you go from E to F, that'll cost you 3. And from F to E will cost you -6, which means the total summation is negative number, which is -3. Well, that is unfortunate because you can go infinite many times so that the you can have lower and lower weights. The more you go, the lower total weight summation is lower. So that means no shortest path is defined in this case. Okay. Um, so we have to use this negative infinity to indicate the shortest path weights for these vertices. Okay. Um, yeah. So hopefully this example shows the specialty about negative weights edges. So actually, the first algorithm we will cover, which is Bellman-Ford, will detect whether the negative weight pass negative cycles exist. Okay. So another thing we want to um, pay attention is that the negative weights can actually exist. Okay, we don't need to like make sure that there's no negative weight at all, but the the cycles is actually something that matters more. Okay, because uh, the summation of all the weights, all the edges in a cycle will be either infinitely big or infinitely small. So in terms of the question of whether a shortest path can contain a cycle, we will say that it cannot contain a negative weight cycle because we already seen that we can go infinitely negative, which means the shortest we cannot find a minimal value, nor can it contain a positive weight cycle, right? Because if we removing the cycle from one path from the path will produce a path with the same source and destination vertices and the lower path weights. Okay, so these are the complexities that we want to avoid. Okay, so in when we want to find the shortest path in this lecture, we assume that there are no cycles. Okay, and no cycles means that all the passes are simple passes. We don't take into those cycles into consideration. All right. So the cycles are something that we will not, um, we don't want to include into the shortest path problem. Okay. Now here we will talk about how we represent the shortest path. So we will use a similar way as the breadth first search tree, BFS tree. So in a BFS tree, we use the number in the vertex to indicate the distance from a target vertex to the source vertex, right? So given a graph, we can actually maintain for each vertex we should maintain a predecessor or a parent v dot pi, okay? And this v dot pi points to another vertex, or it can be nil or can be none for the source vertex. So the from v to the edge from v dot pi to v actually connects these two nodes, connected these two vertices. Okay. So what we need to do is to set the pi attributes so we can use the chain of predecessors for a vertex, and we can follow that chain backwards along a shortest path from S to V. Okay, so these uh, like the tree edges in the shortest path tree will give us the shortest path from the source to any vertex. Okay. So a shortest path tree is just like a BFS tree, right? But it contains the shortest path from the source. Again, here we want to emphasize that this is uh, the path is defined in terms of the edge weights in term, instead of the numbers of edges. Anyway, so far we have laid out all the notations that are relevant to the algorithm. Okay, so when we start introducing the algorithm, we will start by this basic operation called relaxation. Okay, so this relaxation is an operation, or you can think of a procedure or a function that is applied to between two vertices. So it's a very basic, a very simple function. And most of the single source shortest path algorithms rely on this simple operation called relaxation. And basically, all the two algorithms we discovered, we will talk about Bellman-Ford, Dijkstra's algorithms. They all call the relaxation operations repeatedly. Okay, it's like a optimization, or it's like a repeatedly run algorithm that calls one operation for many times until all the edges are have been covered. So let's look at the definition of relaxation and why it will help us find the shortest path. Okay, the relaxation, in order to understand what it does, so we will introduce a new attribute for the vertex in the graph. So previously we introduced the pi, which is to connect from one vertex to its predecessor or to its parents and so on, right? So this attribute called d, okay, so this is some real value in d, real number d, and it is an upper bound on the weights of shortest path from S to V. Okay, so it's not necessarily the shortest path after we initialize it, right? It can be initialized to infinity. For example, it can be initialized to a very big number, so that it's always the upper bound for the shortest path from S to V. Okay, but our goal is to use the V dot d to store the possible values for the shortest path. So we can call the d a shortest path estimate. So it can be in some estimation for the shortest path. It's not necessarily true, and we can initialize them to um, infinity. Okay, so or simply for each vertex in a graph, we will initialize the d to be infinity because we don't have any information yet. Okay, and all the pi to nonce because no path is found yet. And the only exception is for the source because the destination from itself is 0. So we call this initialize single source procedure. So this procedure will be constantly called or will be constantly used in Bellman-Ford and the Dijkstra. So before we run any single source algorithms, we need to initialize all the D's for all the vertices. Okay, so having this D, we can define the operation of relaxing. Okay, so the process of relaxing is actually applied to an edge. Okay, if we want to relax an edge from U to V, we basically, what we are doing, excuse me here, what we are doing is to test whether we can improve the shortest path to V by going through U. Okay, so so first of all, a shortest path to V is from S to V. Okay, so our S is always predefined because this is a single source. Our S is always fixed. Okay, so for the path from S to V, that estimates for this shortest path is stored in V dot D, right? Which is initially infinity. And we will test whether we can improve this shortest path by going through U, right? By going through U means that we will start from S and we'll go to U first, and then from U to V by including this edge from U to V into the shortest path from S to V, okay? So if so, then we need to update the D values and the pi values for V, okay? Because it tells us that from S to U, so S on the left, U in the middle, and V at the end, okay? So if the V dot D is can the so the if the U dot D plus the weights of this uh, edge between U and V can be a smaller value than V dot D, then that means we should go to U first and then go to V, right? So that is the very basic examination. We just compares uh, the value, we just use the values of the edge weight from U to V and the original value of V dot D and U dot D to compute, to determine whether we need to update the value for V dot D and V dot pi. Okay. All right. So a relaxation step may decrease the value of the shortest path estimate V dot D and update V's predecessor attribute. So this is what the relax procedure looks like. So it takes into the U vertex, the V vertex, and the weights function. So W, remember that W is not a vertex, W is a weight function. And it will check, use a if statement to check whether V dot D is greater than U dot D plus the weight between U and V. And if this is the case, which means U dot D plus W plus the weights is a better option, is a shorter path, then we need to update V dot D, okay? Because the old V dot D might from another path, but not going through U. But now, because we found that if we go through U first, it will result in the shorter path. So why not? We just go through U first. So we will update the D of V with this new value, U, which is U dot D plus the weight between U and V. And then we also update the pi relationship because the parents of V should be U. And any kind of shortest path algorithm will call the initialization function, initialize single source function, and then repeatedly call the relax on the edges. Okay, so a relax will be repeatedly called on all the edges. So this is something in common between Bellman-Ford and the Dijkstra's algorithm. Okay, and relaxation is the only means by which the shortest path estimates, so which is the D, and the predecessors, which is pi, changes. Okay, so outside this relax procedure, there's no place that this D or pi will be changed. Okay, and the algorithms, for example, Bellman-Ford and Dijkstra, only differ in how many times they relax each edge, and actually the order in which they relax edges. Okay, so that is the uh, uh, essential difference between the two algorithms. Okay, so let's look at a couple of the properties for shortest path and the relaxation. Okay, so the first one is called the triangle inequality. Okay, it's maybe similar to the triangle inequality about triangles that we learned in high school mathematics. So it says for any edge in the graph, we must have that the shortest path weight from S to V should be less than or equal to the first segment from S to U and the second segment from U to V. Okay, and the second is called upper bound property. Okay, we must have that the estimates v dot d must be greater than the theoretical minimal point, the minimal value, which is delta from S to V. It must be true to all the vertices. And once the estimate v dot d achieves the theoretical minimum point, it will never change. It will never go up. Okay, so the relax process is a one-directional process. We can only decrease the values for the minimal for the shortest path weight, but we can never increase it. Okay. All right. And some other properties. The first one is called no path property. Okay. Then if there's no path, then we can define with that estimate always remain the infinity. And the next one is called path relaxation property. Okay. So if a path from V0 to Vk is the shortest path from the source, and then we relax the edges along this path in such an order. Okay, if we relax the edges in such an order from V0 to V1 first, and then from V1 to V2 first, until we reach the last point, the last edge from Vk minus 1 to Vk. If we relax all the edges in such an order, then we must have that the D property for Vk is the theoretical shortest path weight from S to Vk. This is a quite useful property because it basically tells us how do we find the shortest path from S to Vk. Okay, it says as long as we relax all the edges in such an order, it's guaranteed that we will have the shortest path from S to Vk. So this property will hold regardless of any other relaxations that occur. Okay, that means we can, for example, relax V0 to V1 first, right? Then we can probably, before we relax V1 to V2, we can probably relax V2 to V3, right? For example, we can insert any other relaxation steps between these blue segments from V1 to V2. So as long as V0 to V1 is relaxed, and then after that V1 to V2 is relaxed, and afterwards, as long as we make sure that all the edges are relaxed along this sequence, then we will make sure that the resulting delta will be obtained. Okay. So these are quite useful. We will use this to kind of prove that the Bellman-Ford algorithm is correct. Okay. And the convergence property, which says that if S to U and U to V is the shortest path, right? And the estimates for U dot D will be the delta at any time prior to relaxing edge U and V. Then the D of V will reach the theoretical minimum value at all times afterward. Okay, so this is also a useful property, which means that we need to, as long as we reach the minimum point for U, and then after relaxing the edge from U to V, we will also reach the minimum points for the theoretical shortest path for the connecting vertex V. Okay. All right. So I think we have laid out all the basic operations and the basic properties for the relaxation property for the relaxation procedure. But unfortunately, I have to stop the lecture. I have to end the lecture today earlier than usual because I have a meeting at 3 o'clock. So I think we will leave the content to after the Thanksgiving break. So we will cover the Bellman-Ford algorithm and the Dijkstra's algorithm after we um, come back from the break. Uh, I will double check the deadline for the assignments. So if necessary, I can probably make some videos about Bellman-Ford and Dijkstra first. Yeah, so I would encourage you to go through the relaxation parts for the textbook on the textbook. So it will contain more detailed explanations to what these properties mean. All right, so